To be effective, modern software applications require access to a constant, unstructured flow of real-time data, drawing from petabytes of external context. Building autonomous AI agents amplifies this requirement. An agent is only as useful as its ability to reliably read and interact with external real-world data states. Historically, developers solved this data retrieval problem through brute force. They wrote bespoke, custom API wrappers to connect a specific large language model to a specific data source. This network graph illustrates the core mathematical friction of that approach. A single LLM needs a direct line to a single database. This is a one-to-one integration. But scaling requires pulling data from multiple places. Adding distinct relational databases forces engineers to write and maintain new, rigid dependencies for each one. Unstructured data sources, like NoSQL databases or local file systems, require their own distinct connection logic, further crowding the architecture. By the time an engineering team integrates external SaaS APIs and local IDE components, the architecture has expanded into an unmaintainable spaghetti network. This is the M times N integration complexity problem. This resulting network is tightly coupled and highly brittle. If a single endpoint changes its authentication method, the specific hard-coded wrapper completely breaks and the agent fails. Bespoke integration creates a fundamental architectural bottleneck. It makes the secure, reliable scaling of complex AI agent ecosystems nearly impossible. The Model Context Protocol, or MCP, is an open-source standard built to bypass this exact bottleneck. At its core, MCP operates as a universal transport layer, standardizing how AI agents communicate with the outside world. By introducing a standard protocol layer, the architectural load shifts. Instead of every new node multiplying the integration work, each component connects once to the protocol, reducing the complexity of the entire system to a constant time effort. By adhering to this protocol, any connected agent can instantly communicate with any compliant data source without requiring a single bespoke wrapper. The underlying mechanism driving this efficiency is a strict architectural decoupling. The application interface is completely separated from the data retrieval logic. MCP abandons hard-coded custom integrations entirely, replacing them with standardized client-server communication. This block diagram breaks down the strict three-tiered blueprint of the MCP standard. The top layer is the MCP host. It contains the user application, runs the MCP client, and is entirely responsible for managing the connection to the large language model. The bottom layer is the MCP server. It maintains local connections to external state, handling specific logic to query databases or fetch data from APIs. Between them sits the protocol itself, the decoupled transport layer allowing host and server to exchange standardized messages. This architecture enforces strict boundaries. The host handles all LLM interaction, but it is architecturally forbidden from directly touching the database. Conversely, the server executes the raw data queries, but it is architecturally forbidden from formatting the final user interface. This separation of concerns forces a highly modular system, eliminating the tightly coupled codebases that previously throttled agent development. To see how this architecture operates in practice, consider a user submitting a complex prompt, asking an agent, "How many active customers do I have?" In this sequence diagram, we see the immediate first step. Before touching the language model, the host must discover what capabilities it has access to. It pings the server layer. The connected MCP servers reply with a list of available tool schemas. The host takes the user's original question and packages it together with these retrieved tool schemas. It then sends this complete unified context package out to the large language model. Notice that up to this point, no external database has been queried. Only structural schemas have been evaluated. The LLM processes the context and replies to the host with a specific decision on exactly which tool it needs to answer the prompt. This dynamic tool discovery allows models to safely understand and adapt to whatever servers are currently available on the fly, entirely bypassing the need for hard-coded access logic in the core application. The host now knows exactly which tool needs to be activated to retrieve the customer count. It routes the specific tool call request down through the MCP protocol layer directly to the correct MCP server. Here, the server takes over localized responsibility. It receives the generic tool call and translates it into the specific SQL query required. The server executes the query, extracting a raw data payload. Once successful, the server returns the raw data payload back up through the protocol transport layer to the waiting host. The host feeds this raw database payload back out to the LLM. The LLM processes the raw data, synthesizes it into a human-readable answer, and returns it to the host, which displays the final result in the application interface. The protocol layer successfully orchestrated a complex database read, keeping the language model abstracted from database credentials, complex networking logic, and query languages. Zooming out from a single execution trace to a macro system design perspective, the economic advantages of this decoupled architecture become clear. Looking at the system broadly, this diagram illustrates server modularity. A single MCP server built for a specific database can be instantly utilized by entirely different host applications. Developers no longer need to write a new integration just because they switch from interacting via a chat UI to an IDE code assistant. The same modularity applies to the host layer. A host ecosystem can expand its capabilities seamlessly. Adding a new database to the system merely requires spinning up an MCP server for it. This requires zero code changes at the host level and zero changes to the underlying LLM. This dictates the new engineering economics for agent development. You write the data integration exactly once at the server level, granting immediate, standardized access to any MCP-compliant client. Standardizing this connection process reduces the accumulation of redundant code and shortens the path to deployment for enterprise agent systems. The Model Context Protocol establishes a standard that replaces manual API wrapper maintenance with protocol compliance. By enforcing a strict architectural separation of host, protocol, and server, systems remain scalable, secure, and highly maintainable as they grow. Even if an engineering team is not building the core AI agents themselves, providing MCP servers for proprietary internal data will soon become a necessary requirement for allowing external clients to interact with that data. This ecosystem matrix illustrates diverse hosts and localized servers exchanging standardized packets, providing a stable backbone for high-volume data retrieval. By removing these integration bottlenecks, the protocol provides the technical framework necessary for building reliable, interconnected AI systems.